I begin, I just want to again encourage anyone to ask questions if you're confused or if you have even just tangential questions. I noticed there weren't many questions yesterday or in general. So as a form of bribery, I'm offering a gift of a free hat, free the Zouche hat, for the most interesting question. And the criteria for most interesting is to be determined later. Okay. All right. So a free hat's waiting for you, maybe. Okay, so I just want to begin by briefly reviewing some of the main ideas from yesterday. So I explained that a lot of people are interested in building quantum interfaces between light and atoms or atomic ensembles. And one of the key ideas is that our standard quantum equations or Maxwell-Bloch equations to describe these interfaces, so a realistic theory necessarily has to simplify something. And it happens to be that our textbook equations make the simplification that wave interference and multiple scattering don't matter. So that manifests itself in two ways. So first, in the Maxwell-Bloch equations, you basically smooth out the atomic density. So you don't worry about exactly where the atoms are, whether the positions even matter. And second, you assume that if you have excited atoms, these atoms emit independently into free space, into 4 pi. But if emission of light is a wave phenomenon, if there's interference, fundamentally that can't be true. The true emission has to involve correlations, spatial correlations and non-local correlations between atoms. And so that's kind of true kind of abstractly, but then you might also ask, can interference be a new resource or untapped resource for applications? And then if you have a theory that includes interference really at the quantum level, can you uncover new quantum phenomena? So then I introduced one possible theoretical framework, a so-called quantum spin model, where in principle such effects are included. So basically, the spin model encodes atom-atom interactions, where the type of atom-atom interaction is such that if one atom is excited and another one is in the ground state, they can just flip each other. That's due to the process of photon emission and reabsorption. And then the strength of that interaction between atoms I and J is just given by the electromagnetic Green's function, or how a photon propagates from one point to another. The nice thing about the spin model is that all the real degrees of freedom are just encoded in the atoms. So if you can imagine that I can solve, for example, the dynamics of the wave function or density matrix under this Hamiltonian, if I can construct all the atomic correlation functions, then I can construct all the correlation functions of the total field for free. And that's because I can formally rewrite the total field as a coherent sum of the input field, whose properties I presumably know, and the correlation functions of the atoms themselves. So then I just proceeded to try and use this spin model for one simple example. So I took a 1D chain of atoms in free space, in 3D, and I considered the limit of a single excitation. So what we found then is, if you have in the limit of an infinite array, then these single excitations will be diagonalized by block states. So you can calculate a band structure for these block modes. And interestingly, if the lattice constant of this array is below lambda over 2, then you necessarily have the appearance of some of these block modes, which have a k vector bigger than that of free space, bigger than omega over c. So what that means is that these collective spin wave excitations can't couple to radiation fields, and therefore they'll have exactly 0 decay rate in the infinite system limit. So an atom is excited, but you'll never lose it in the form of emitted photon. And then finally, if you kind of go to a finite case, you see that a lot of the kind of same physics still persists. So if I just take 30 atoms and calculate the most subradiant eigenstate under this Hamiltonian, and then I go and plot the fields, you see that basically in the bulk you see no radiated light. So basically along the bulk, the light is being wave-guided by this array. And then when you hit the end, you get a little bit of end-fire emission. That's exactly what you would see if you just take a normal optical fiber and you cut one end. Okay, so I think last time I concluded by saying that once I have if I can create a subwavelength array, I'll naturally create these subradiant states or have their existence, but it's going to be hard to couple to them or see them in general. And the intuition is basically the following. When I say that I see some optical property of an atom, what it means is I usually shine in a laser and see, try to look for some effect. But by definition, a laser is a radiation field, so no matter which direction I send it in from, it's always going to live within this so-called light cone. So k is always going to be smaller than omega over c. But then the states I'm trying to access, these subradiant states, live outside of the light cone. So the wave vectors of the laser field and these subradiant states are fundamentally mismatched. Okay? So it's kind of interesting. So even though this is kind of for an array, I think at least qualitatively a similar story is true for just disordered ensembles as well. I think subradiants generally exist in any kind of atomic ensemble, but it's very hard to see experimentally just by some type of this kind of impedance mismatch. But the special thing about arrays is that subradiance now acquires a very physical, intuitive meaning. It's really nothing more than this chain of atoms is acting like some kind of fancy waveguide or optical fiber. So once you realize that, then you can try to cook up efficient ways to couple to these guided modes. And one way to couple to guided modes is by using another set of guided modes. And just to make that more specific, here I'll consider an optical nanofiber. This very thin fiber still guides light, but essentially to obey the diffraction limit, now a lot of the light so to obey the diffraction limit, a lot of the light actually kind of leaks evanescently out of the fiber core and into the surrounding vacuum region. So realistically, this kind of evanescent field into the vacuum can extend several hundreds of nanometers. And that's useful for interfacing these guided modes to light. So for example, one thing you can do is you can shine in light that's very far off resonance. This far off resonant light will simply act as a trap for atoms. You can do even better and send light both ways, so that creates a kind of standing wave pattern and an optical lattice. So that allows you to trap atoms periodically very close to the fiber. And then once atoms are trapped there, if you send in near resonant light, the atoms will interact very efficiently with that light, essentially because the guided modes are still relatively tightly confined. You have a very small effective area. So experimentally, even though you have an optical lattice, you still have to fill it. Experimentally at the moment, people tend to get around 50% filling of the lattice sites. So it's not a perfect lattice. In the kind of theory, we want kind of 100%. But there's kind of efforts underway to try and improve this 50% filling factor. And finally, just to quantify this notion of efficient coupling, one way to quantify that is imagine I have just one atom trapped near this nanofiber. I bring it up to the excited state, and I want to calculate the collection efficiency or the branching ratio. So when that excited atom emits a photon, with what probability does that photon emit into the guided modes of the nanofiber, gamma 1d, compared to the emission rate into free space, into 4 pi. And it turns out for kind of conventional nanofiber interfaces, that fraction is about 5 to 10%. So let's just kind of experimentally fast forward a bit. Imagine soon that you can kind of create small ordered arrays with no kind of empty sites of atoms near a nanofiber. So let me just kind of redraw the dispersion relations of the guided modes of the individual systems. So the blue curve here was the single excitation block modes of just the atomic chain alone. And again, the interesting states are these kind of subradiant states with a k vector beyond the light line. Now, a fiber mode, if it's guided by definition, it's also going to have a dispersion relation that lives beyond the light line. So k is always going to be bigger than omega over c. And then kind of generically, if you create such a system, the fiber dispersion relation and the dispersion relation of these kind of atomic spin waves are going to intersect somewhere. And once they intersect, these fiber modes and these kind of atomic chain modes can efficiently interact with each other. They're now impedance matched. So if they're impedance matched and they can efficiently interact, then I kind of slightly changed the topic on you guys. So now this kind of atomic mode, which is efficiently coupled, will no longer be subradiant, right? Because if you have this atomic excitation and it sees modes to couple to, it'll simply emit a photon into those guided modes. So it'll no longer be subradiant. For lack of any other term, we call it selective radiance. But it turns out if your goal is to build an efficient atom-light interface, that's perfect. That's exactly what you want. What I mean by that is, if you imagine creating one of these kind of atomic spin wave modes that's impedance matched, then this mode will emit efficiently into the waveguide. So you'll experience collective enhancement. So basically, this single collective excitation will no longer emit at a rate gamma 1d into the fiber, but at a rate n times gamma 1d, even though it's just one excitation, but shared among n atoms. So recall that this kind of collective enhancement is a key ingredient or key feature of just atomic ensembles in free space as well under the Maxwell-Bloch equations. So this kind of collective enhancement is nothing kind of new or special. What's special is that because I have the spatial ordering and because this particular collective atomic mode has a k vector that's bigger than that of free space, I can at the same time that I get collective enhancement into the good guided nanofiber modes, I can get a collective suppression of emission into the bad free space modes, which are hard to collect. So interestingly, one might expect that this kind of emission rate into free space will actually become suppressed as a function of atom number. So you might remember yesterday, if I just had a chain of atoms in empty space, the most subradiant mode had a decay rate that decreased like 1 over number of atoms cubed. Okay? So basically, if I think about the light as carrying quantum information, this quantum information is good because I can collect it and send it to other places. This quantum information that's just lost into free space is bad. And what dictates the kind of fidelity of applications one would expect would be the branching ratio of n times gamma 1d over gamma prime. So recall that if I assume independent emission, like in the Maxwell-Bloch equations, then gamma prime is just independent of n. It's just the single atom emission rate. So this ratio becomes the optical depth of the medium. It's linear in the number of atoms. And then the point is by exploiting interference in such a geometry, this branching ratio can be much bigger than d. And in particular, it can grow super linearly, maybe like n to the 4th power in the number of atoms. So we can use this kind of extremely favorable branching ratio to try and beat the usual error limits set by the optical depth in various applications. So is that kind of key idea clear to everyone? Okay, so I'll shortly go and analyze one particular application. But to say that we can do better than the old equations, we have to actually set up kind of an artificial model of an atom nanofiber interface that has the same assumptions as the Maxwell-Bloch equations. So in particular, I'll refer to this kind of hypothetical model as the independent emission model. So basically, we have a chain of atoms that are coupled to a fiber. We'll assume that they can emit efficiently into the guided modes by collective enhancement. But then just kind of by hand, I'm going to say that they emit into free space independently and at a fixed rate, gamma naught. Okay, so this is essentially the Maxwell-Bloch equations, but now adapted to the nanofiber system. And then I want to compare that to the collective emission, where I now use my kind of spin model to account for interference in all directions, both into the waveguide and into free space. So to do that, I again just go back to the spin model. Yesterday, I talked about this kind of quantum spin model just in free space. Okay? So it turns out it's pretty easy, at least in principle, to adapt to a nanofiber. So the only thing that changes in the spin model is that instead of putting in the electromagnetic Green's function for free space, you should put in the Green's function for a nanofiber system. So physically, this Green's function is nothing more than, so this Green's function says if I put an oscillating point dipole at position, let's say Rj, what's my total field, radiated field, at another position, let's say Ri, but now accounting for the dielectric perturbation of the nanofiber in vacuum. And above all, this Green's function for the nanofiber will include the possibility that this oscillating dipole at one point will launch guided modes into, will excite the guided modes of the nanofiber. And similarly, I can just straightforwardly adapt this kind of input-output equation. I just have to replace the electromagnetic Green's function of free space with that of the fiber. Furthermore, if we take a cylindrical fiber, you can use basically the symmetry of the system and actually analytically solve for the Green's function in terms of Bessel functions. So I said that when you can solve for the Green's function, I think that means kind of in principle. Okay, so it's really just an exercise in pages and pages of Bessel functions. So it's not something that you want to do, but if you're lucky, you can find a postdoc who will do it for you. They might not be happy about it, and they might not want to talk to you later, but they'll do it. Okay, so that's kind of formally how we adapt the this kind of spin model to the nanofiber. And now let me talk about a particular application. So I kind of alluded to it yesterday. So I'm going to talk about a photon storage or a quantum memory for light. Just to remind you of the point of this application, if I have photons, that's a convenient way to transmit quantum information over long distances. So for example, I could imagine encoding a qubit in either the polarization degree of freedom of the photon or in some kind of timing, like it can arrive early or late. So while photons are good to transmit information, they're not really good to kind of store information. Right? Imagine that the information in your hard drive was flying around at the speed of light. Right? It'd be very hard to kind of retrieve in any sensible form. In quantum mechanics, we have the additional difficulty that if we have some kind of qubit, we can't just go measure it and copy it in order to store the information. So what we can imagine doing instead is just sending that entire quantum wave function of the photon into, for example, an atomic ensemble. This photon might coherently excite the ensemble. So now I'll have some atomic wave function where one atom is excited in some certain superposition. So now I've converted a flying photon into a kind of stationary, a qubit or stationary excitation. And ideally, this is a quantum coherent process, or there's really some kind of unitary map that describes this dynamics. So the reason I kind of focus on this particular application is that it's really still in the single excitation limit. I'm really only interested in storing a single photon. So we can just directly extend our previous calculations and concepts. It's maybe a bit of a technical point, but I want to clear up some potential confusion. So I also mentioned yesterday that if we deal with this spin model in the single excitation regime, it's completely equivalent to classical linear optics. It's like the physics of classical coupled radiating dipoles. So maybe it's kind of strange that the physics is classical, but I'm calling it a quantum memory or quantum application. So it turns out it's no paradox. I mean, that's just because the memory itself ideally is just passive, right? I mean, the whole goal of the memory is you have a photon qubit, you give it to me to store, and at some later time I just give it back to you. So I'm not manipulating the qubit in any way. In particular, I'm not creating any more entanglement if there was no entanglement to begin with. So in this case, the quantumness really just comes from the fact that this qubit itself could be quantum. It could be entangled with other degrees of freedom. But that entanglement was created by external sources. Okay, so it's a quantum application, but it's kind of classical in its understanding. Okay, so this quantum memory should be it should work both ways. So I should be able to convert a photon to a stationary atomic excitation, but then at some later time, I should be able to reverse it and convert it back to a photon, right? That's how a hard drive should work. So it turns out by time reversal symmetry, the error probability by error, I just mean when you try to store a photon or when you try to retrieve it, there's some probability they just lose the excitation altogether. So that error probability is going to be the same in storage and retrieval. Okay? And I say that just because it's easier in practice to optimize the retrieval process. So in other words, if I start with some collective single excitation, it's easier to calculate what's the probability that I get a guided photon coming out. The reason it's easier is because here I explicitly have kind of atomic degrees of freedom, atomic excitations, and my spin model is really in terms of atomic excitations in the first place. Also, just a bit of a technical note, maybe for those who work with quantum memories or know of quantum memories. So technically, this kind of system, so here I kind of assume that the atoms are two-level. It is a quantum memory, but it's not a very practical one. What I mean by that is, when you send in the photon, it'll coherently excite, or the atoms will coherently absorb this photon. You'll generate, atomic excited states. But then if your atoms are excited, they'll simply just kind of spontaneously emit again. And the emission can be, super radiant or subradiant. But the point is you have no control over the timing, right? That photon is just going to be spit out at some, fixed time that you can't control. So to fix that, in practice, when people build kind of practical quantum memories, they typically go to some kind of EIT or three-level scheme. Basically, you still have the kind of two-level structure, G to E, which is coupled by the waveguide photons. And basically, the idea is you introduce a third level. This can be a second ground state or some metastable state that lives for a very long time. And the idea is that, as the photon comes in and you start to excite population into the state E, you basically apply a second laser field, just a control field, to kind of siphon off the population from state E and kind of shelve it in this long-lived state. And if that state kind of lives forever, then when you're eventually ready to kind of retrieve that photon, you simply turn on this field again, bring population up to E, and leak it out in the form of a photon. So this is a practical quantum memory. But it turns out if we just, in terms of kind of mathematical efficiency, the error is the same. So I can analyze the error of this kind of unpractical two-level quantum memory, and I basically get all the physics that I want. Okay. So that's what I'm going to do here. Okay, so let me just kind of qualitatively describe how we can analyze the quantum memory. So the numerical procedure goes something kind of like this. And I say numerical procedure because I just kind of want to emphasize that even though you haven't worked with the spin model, most of you haven't not worked with the spin model before, maybe it looks a little abstract, it's just kind of n-coupled equations. So yeah, mathematically it's something that you can easily just plug into your computer. Okay, so what we do is we want to analyze the retrieval process. So we assume we have a single excitation, but which is stored in a kind of superposition of different atoms. Okay. Then what we want to do is we just want to calculate the Schrodinger equation time evolution of the state under this effective spin model Hamiltonian. Once you have the state at all times, you can calculate the probability that a photon was emitted into the waveguide. That's going to be basically the time integral of the power, the intensity of light emitted into the guided modes, integrated over all time. So that gives you kind of a total energy. And if you normalize that energy by the energy of one photon, h bar omega, then you finally have the probability of emission of a photon into the waveguide. And then the next thing you can do is simply optimize over all the amplitudes Cj to get the maximum retrieval probability or retrieval efficiency. So in practice, in concept, that's kind of all there is to the calculation. In practice, you can actually kind of speed it up quite a bit. So instead of trying to really optimize over this massive dimensional parameter space, you can formally kind of play some mathematical tricks and turn it into an efficient optimization algorithm. Okay, so let me just kind of show you the results. Here's the retrieval or storage error in this kind of in this array nanofiber interface as a function of atom number. So the red curve here is actually just the independent emission model. So it's basically the kind of Maxwell block equations. And you see that the error, at least once you go to high atom number, scales kind of inversely like the number of atoms, like 5.8 divided by optical depth. It turns out this kind of asymptotic scaling is exactly the same one that's derived for an atomic ensemble in free space under the Maxwell-Bloch equations. Alternative, you can really account for wave interference into all directions. And then when you do that, you find this kind of new scaling where the kind of error scales like 1 over n squared. So really, we found a better error bounds than was fundamentally thought to be possible. Just by, again, exploiting the power of interference. So that sounds kind of cool, that we kind of, beat, something that people thought was quite fundamental. But at the same time, maybe we can be a little bit greedy and say, well, this 1 over n squared doesn't really seem that great, right? It doesn't seem ideal. And what I mean by that is, one of these factors of n will automatically come from collective enhancement, so just enhanced emission into the guided modes. That already occurs in even just the Maxwell-Bloch equations. So essentially, we're only getting an extra factor of n from the suppression of emission into free space. And that doesn't seem so great because, as I kind of showed you yesterday, if I just take a chain of atoms in free space by itself, the most subradiant mode, so I can suppress emission into free space, actually by amount 1 over n cubed. So it seems like we're losing factors of n somewhere. And so, yesterday and today, I spent a lot of time just trying to introduce classical intuition. And now we can see how all that intuition can pay off. Okay? Basically, what I guess the kind of key points that I try to argue is that, if you have just a kind of nanofiber or waveguide by itself, in principle, that thing is perfect. Right? It'll guide light forever, and you'll never lose a photon into empty space. Similarly, if I have this kind of composite, kind of fancy fiber, where I have a periodic chain of atoms coupled to a real nanofiber, that thing also, in principle, can guide light perfectly. Right? You'll never lose a photon. So it's basically like I have a perfect bare nanofiber. I have a kind of perfect composite fiber. And so now, if people, I guess people who work in optics labs, I guess you'll know that, if you have two different kinds of fibers, both of them are perfect on their own. They both perfectly guide light. But if you want to connect them, if you just kind of put them one against each other, you have a problem, right? Because generically they have different kind of spatial modes. They'll have different dispersion relations. So basically, when light guided in one region tries to enter the new fiber, it sees an impedance mismatch. And you get a lot of loss just at the interface. So the interface scatters the light into free space. So you might believe that this kind of interface scattering is really the origin of this kind of moderate gain from this kind of subradiance. So basically what you need is you need to buy a fiber. Sorry. Yeah, it's a numerically observed scaling. Yeah. So basically, I evolved my atomic state under H effective. So this describes, in principle, the loss of atomic excitation due to emission of photons, either into the fiber or into free space, but it fully includes interference. So basically, the loss is basically the part of the emission that goes into free space as opposed to the fiber. So if I can calculate how much light goes into the fiber, let's say I can see it's 99%, then I can automatically include, say that the loss was 1%. So the way I do that is I can, in principle, through this input-output equation, calculate the light going anywhere. So I can just calculate the fraction of light going into the nanofiber. And from there, I can extrapolate how much is lost. Does that make sense? Oh yeah, so it's the system is it's an infinite nanofiber with a finite atomic chain coupled to it somewhere. So yeah, it has no kind of symmetries of an infinite system, right? It's really just a hard cut. Yeah. Yeah, yeah. Yeah, so because my real simulation is kind of a realistic system, it has these hard edges. Those hard edges can give rise to scattering by themselves. Yeah.
And when you say then you optimize on the output of the interface.
Yep.
How do you do the
Yeah, so that's actually kind of tricky. So basically the issue is, for these simulations, you see I have up to 200 atoms. So in principle, I have 200 parameters that I should go and optimize. We haven't tried to do that explicitly, but my guess is it doesn't work so well. I mean, you probably can find local minima, but maybe not the real minima. So it's a little bit, I mean, there's no way to kind of argue it's true intuitively, but mathematically, it turns out you can cast this whole optimization into an eigenvalue problem of a Hermitian matrix. So I can formally encode the error probability into the eigenvalue of a Hermitian matrix. And so basically I just have to go and diagonalize a Hermitian matrix, which is efficient. Okay. So that's not obvious at all, but it just happens to be true. Okay. So basically I need to buy some kind of fiber connector. And a fiber connector connecting to atoms is not something you buy from Thor Labs. But we can just kind of create one on our own. So our kind of fiber connector is not really going to be any kind of physical device. But if we now just kind of go from a 2-level system back to a 3-level system, recall that I can use this, I have this kind of external pump field where my goal is to kind of shelve population from this excited state into some long-lived state. So basically I can start playing with this spatial shape. Okay, so maybe I can make the intensity very big at the edges and smaller in the middle of the chain. So to understand why that might be good, this is a little bit technical, but if you're familiar with electromagnetically induced transparency, you know that the amplitude of the control field dictates the bandwidth of the transparency window. So as you make the control field bigger and bigger, it's effectively like your atom becomes more and more transparent to the light. It's almost like it doesn't exist. So essentially what we're doing is we're turning on the atomic response slowly. It's like this atom is physically there, but in terms of a response to light, it's effectively not there. And this atom has a little bit of a response, this atom has more response, and so on. It's kind of like an adiabatic transition from an empty fiber to this composite fiber. Okay? So I smooth out this discontinuous interface. So now I repeat the calculation, and surprise, there's not even kind of a 1 over n to the 4, but I find an exponential suppression of error with atom number or with the optical depth. Okay? So to just kind of summarize the results up to here for this nanofiber. So okay, everything I did was kind of single excitation, so all the physics I can understand classically. Nonetheless, we still found an exponential gain for a genuine quantum application, that of a quantum memory. So this is admittedly a very personal view, but it's kind of like, once you smell kind of exponentials, how do you ever go back to what how do you just go back and accept what you learned in textbooks? It's like, let's keep digging and find out what the real answer is in a broader context. So that's what really kind of drives my interest in this kind of multiple scattering and wave interference. I honestly don't believe that the limits that we know about today are anything close to what's real. So the next thing I want to do is provide a kind of similar example where we can get a gain by exploiting interference, but I want it to be a genuine quantum application. So it's not going to be physics that we can completely understand in terms of classical physics alone. Any questions up to here? Yeah, I mean, so it's not easy. So I think generally what it illustrates is the spin model. If you know what parameters you're using, like I know the control field and lattice constant, it's just you should view it as some kind of numerical black box, right? You put in stuff, you get the right answer, but you don't necessarily understand why. You notice that like a lot of the intuition I provided was kind of independent of the spin model, right? It's just kind of intuition from classical optics and so on. So what you really have to do is just kind of put them together. You use the classical intuition as kind of as guidance to create hypotheses. You use the spin model to kind of confirm that, but it's hard to kind of see it directly from the spin model alone. If you want a little bit more of a specific answer, well, a similar calculation you can do is just if you have this kind of empty, if you just have a chain of atoms just in free space, and you make it 3-level to provide a similar analogy, and then you were to apply in this spin model a control field which varies spatially, you would find a similar effect. So if you look for subradiant modes, you would find subradiant modes whose decay rate is now exponentially small in the atom number. So it does show up in the spin model if you kind of play with it correctly. But I guess the point is, without the classical intuition, you would never think that this kind of spatial shaping of control fields would be good for anything. Does that make sense?
How smooth would you need to do the
I think the details don't really matter. So I think here we just chose rather some generic shape. I think if you start optimizing this shape, you could. I think you would still have exponential, but you could probably make an even steeper curve than what you see here. Yeah. So I think this kind of exponential is robust to the specific shape as long as it's smooth and as long as it's big at the edges. Okay. So I said, next let's try to work toward a genuine quantum application. And I put in the word toward because before I can jump directly to the quantum application, I have to introduce a little bit more classical physics. So it's an example that I also kind of briefly alluded to yesterday, which that if I create a kind of 2D array of atoms, let's say infinite, just for simplicity, that in principle can form a perfect mirror for single resonant photons. So let me try to explain how that works. And later we're going to exploit this kind of reflection to really do something truly quantum mechanical. So the intuition goes something like this. Just for simplicity, so now I've kind of rotated the geometry. The array of the atom array lives in the XY plane. And then just for simplicity, the light that I send in at the beginning is going to be on normal incidence, so in the Z direction. So in general, my light is describable by a 3-dimensional wave vector, which describes the direction of propagation. And at normal incidence, the in-plane component of the wave vector is going to be 0. Okay, so that just says it's perpendicular to the plane. So because of the discrete translational symmetry of the system, I know that exactly the form of the collective spin wave excitation that this plane wave is going to excite. In particular, if the plane wave is weak, so at most there's only one excitation in the system, then I'm going to couple to this kind of collective excitation where one atom is excited with a relative phase e to the I k r, where this wave vector k parallel is exactly that of the light that I send in. So in particular, if I come in a normal instance, all the atoms will be excited in the same relative phase. That kind of makes sense. Okay, so now that I know the form of the atomic excitation, the form of the spin wave that's generated, I think I can think about how that spin wave re-radiates light. Basically, I can kind of take a plane wave decomposition of the light that's re-radiated. And kind of intuitively, one would expect that this spin wave should be able to re-radiate light with a kind of in-plane vector, k parallel, that's exactly that of the spin wave. So if we ignore this kind of vector g for a moment, that's set g equals 0, it kind of makes sense that this spin wave can excite an electric field, a plane wave, with a kind of in-plane component e to the I k r. But then, of course, my electric field lives in 3 dimensions. So this is really just the kind of parallel component of the wave vector. I can have a perpendicular component of the wave vector as well, which describes how the field evolves as you go away from the atomic plane. So that's kind of intuitive that a spin wave of wave vector k can generate an electric field of wave vector k. But because my system has a discrete translational invariance, it's possible that my lattice can add discrete momentum components to the electric field as well. So it's a little bit like a kind of a Bragg grading, if you want. So in particular, in addition to the original wave vector k, I can generate, my lattice can generate additional wave vectors, g, where g is basically any kind of reciprocal lattice vector. So my lattice in general can form a discrete superposition of different plane waves going in different directions. So maybe that kind of description is a little bit mathematically abstract, but it kind of in pictures it looks like this. If I excite the k parallel equals 0 spin wave, then kind of intuitively this spin wave as it radiates can radiate either straight up or straight down, but it can also kind of act as a Bragg grating, diffraction grating, and radiate light into discrete directions. So for example, here you have the first diffraction order, where g is plus or minus 2 pi over d, and so on. So Maxwell's equations dictate that some constraints on the total k vector. So in particular, k parallel plus g squared plus the k perpendicular squared has to equal omega over c squared. So now if we go back to kind of normal instance, if k parallel equals 0, if I specify that my lattice constant is smaller than the optical wavelength, then any value of the reciprocal lattice vector I choose, I'll have that g is bigger than omega over c, or any multiple of 2 pi over d is going to be bigger than omega over c, unless g equals 0. So if g itself is bigger than omega over c, that would force k perpendicular to be imaginary. What that means is that for example, this kind of first diffraction order that I illustrated here would not be a true radiation field, but it would be evanescent. So it can't actually radiate energy away. So to kind of just summarize, if I have a sub-wavelength lattice constant, the field radiated by this atomic spin wave, by this k parallel equals 0 spin wave, can only be normal to the lattice. And clearly it's going to be symmetric. So it'll radiate an equal amount up and an equal amount downward. Okay, so now let's finally understand how this system can create 100% reflection. So imagine that I have an array, and here I kind of rotated the plane a little bit, so the plane of the array comes into and out of the board. So I'm just kind of showing a cross section. I shine in light from one direction at normal incidence. So formally, this kind of configuration here is equal to the coherent sum of two different configurations. So it's one possibility is instead of sending in light from one direction, I send in light from both directions. And the relative phases of these fields are equal. What that means is that in the plane of the atomic array, they constructively interfere and form an antinode of a standing wave. Okay? Plus, I can send in light from both directions, but I can put a minus sign on this field here. That means that in the atomic plane, these incident fields completely destructively interfere and form a node, so the atoms effectively don't see the light at all, or vice versa, the light doesn't see the atoms. And notice that if I add these kind of two configurations up, I finally get a field coming in from this direction, and the fields coming up from this direction cancel out. Okay, so how does that help? Well, let's consider how light scatters from this configuration first. I argued that the light basically doesn't see the atoms at all because the atoms sit in a node. And therefore, each of these individual plane waves will just kind of continue unimpeded past the atomic plane. They'll have a transmission coefficient of 1. This case is a little bit more subtle. So now my atoms are excited because they sit in an antinode of this kind of standing wave. But recall what I said previously. Because this is an infinite system, because it's sub-wavelength, when these atoms are excited, they cannot radiate into random directions or even into other diffraction orders. They can really re-radiate both into the up or down directions. And furthermore, I can't, because I have no energy radiated into other directions, I have to get out all the energy that I put in. So the amplitude of the transmission coefficient has to be 1. But then because if I specify that I'm sending in light on resonance, what happens is a kind of subtle effect. I send in light on resonance. Because the atoms are in resonance, the atomic dipole moments, the induced dipole, that's kind of becomes 90 degrees out of phase with the field. And then the field that this atomic dipole radiates is another 90 degrees out of phase. So basically the field that's re-radiated by the atoms is going to be out of phase with the light that comes in. but I have to get all the light out, and therefore the transmission coefficient has to be -1. Now I can kind of add up these two answers. So in particular, let's consider what's the light coming out from the bottom side. So the light coming out from the bottom is this field here, which is transmitted with a phase of +1, plus this field here, which is transmitted with a phase of -1. So you see they cancel out. I have exactly 0 transmission on resonance. And then I can play the same game to find out what's reflected. And I see the reflection coefficient should be 100%. Okay? So what's interesting is that, I've tried to argue kind of on intuitive grounds that on resonance, an array of atoms will be perfectly reflecting. What's interesting is that up to now, I've never explicitly invoked the spin model, right? It's just kind of intuition and kind of mathematical tricks. So it turns out you can formally derive it from the spin model and combine with the input-output equation, but it's actually much more work. Okay? So again, that kind of illustrates that once you just realize there's interference in the problem, you can gain a lot of intuition without actually having to go through all this kind of spin model business. Okay, so basically what I've established so far is that I can have 100% reflectance of single photons at normal instance once my lattice constant is smaller than lambda. So in principle, you can kind of repeat the same arguments. If you start to shrink the lattice constant even further, then what you find is that there's a kind of increasing range of angles of light that you can send in around normal incidence, where you, again, can't scatter into diffraction orders because they're all evanescent. So basically, then you can achieve 100% reflection for this increased range of incident angles as well. Finally, once you reach a lattice constant of lambda over 2, you can get 100% reflection no matter what direction you send in the light from. There's actually just one important catch, though, which is that this light has to come in on resonance. And when I say on resonance, it's not the bare resonance frequency of an individual atom, but it's actually the dressed resonance frequency of this collective spin wave that you're exciting. And this dressed resonance frequency will in general be different than the bare resonance frequency, essentially because a given atom sees the light coming from all the other atoms, and that introduces some kind of interaction energy. Okay? So what that means in practice is that if you come in, instead of coming in with a plane wave, if you come in with a focused light beam, that focused light beam is composed of a superposition of different k vectors. And that means that because this kind of resonance frequency depends on k itself, you can't simultaneously achieve resonance for all the different k vectors. So you'll see slightly less than 100% reflection, even if you have a perfect lattice. So it turns out that as of a few months ago, this is no longer just kind of pure theoretical fantasy, but this is something that can be experimentally observed, particularly in the Manuel Bloch's group in MPQ. So let me just kind of highlight some of the main experimental results and the setup. So basically, what they do is they create a nearly defect-free 2D array of atoms with subwavelength spacing. They do that through actually kind of complicated setup. That's basically a kind of quantum degenerate gas of ultra-cold atoms. It was something what's called a quantum gas microscope. And basically, the main trick to creating this kind of defect-free array is that they go through, because of atomic interactions, they can kind of go through a quantum phase transition and create something what's known as a Mott insulating state. The specific properties of this Mott insulating state aren't so important, but the main thing to take away is that this Mott insulating state, this phase, is basically guaranteed to have exactly one atom per site. Okay, so you have no defects. So once you create that kind of defect-free array, you can send in light, to reach the atomic array. Some of it will bounce off. You collect that light and you kind of image it on a CCD. And when you do that, you get something like this. So you see that basically exactly where you have atoms, you see this kind of spike in reflection. And where you have no atoms, you see no reflected lights. If you want to be a little bit more quantitative, you can change the resonance frequency, or you can change the frequency of the light you send in, and actually map out a reflection spectrum. You see that basically on resonance, you get a reflectance, in this case of 60%. So it's 60% rather than 100% because of various technical imperfections. But maybe the most important one is that in this particular experiment, it's not really feasible to kind of just send in one photon and then kind of reset the experiment, build another mod insulating state, send in another photon, and so on. That just takes too long. So what they do in practice is they send in they send in weak light. So at any one time, you probably only have one excited atom in your system, but they send in that light over a very long time. So the integrated total number of photons is huge. So that means that any one photon is likely to have scattered any one atom is likely to have scattered many photons. And for those of you who are a little bit familiar with atom trapping and cooling, you know that so an atom is pretty light, and anytime you scatter a photon, the atom can get a little bit of a momentum kick into a random direction. And once you scatter enough photons, that momentum kick really starts to accumulate. The atoms pick up a significant kinetic energy. And so you can really think of it as basically these atoms start to really move around dynamically. And so it looks kind of a little bit like a disordered lattice rather than a perfect ordered lattice. So it's not the only effect, but it's probably a predominant effect why you see 60% reflectance instead of closer to 100%.
Sorry about this. So, but this is an imperfection because the theory says it will be a collective mode, so
So the theory is really only due to, the theory really only accounts for kind of really perfect ordering, so that all the interference from all the different dipoles is perfect. So once you start to displace the atoms, you might think it's a little bit like kind of, if you displace the atoms enough, it's a little bit like kind of what Remy showed, right? You might expect to see kind of speckle coming out, but it's a kind of continuous transition from perfect to this speckle.
could they, when you take 100% reflectance, could they take the negative side of
If you, so I think realistically you would not get 100%. Or let me kind of step you through the other imperfections. So the first issue is really just kind of technical. You send in many photons, the atoms start to heat up and move around. But imagine you can kind of fix that and really just send in kind of one photon. The next issue that's kind of left over is even if so the atoms sit in a external potential, a trapping potential, but the atoms are still relatively light. So even if they're in the ground state of that trap, there's still a quantum 0-point motion that's left over. So it's not huge, but it's some non-negligible fraction of the lattice constant or of the free space wavelength of light. So how that quantum 0-point motion enters exactly into the scattering properties, that's actually still a little bit of an open question. So to lowest order, you might maybe kind of one toy models, you can say, well, maybe in terms of light scattering, it's maybe like just kind of classical position disorder. So maybe that's true, maybe it's not. But the quantitative effect of quantum motion has not really been kind of elucidated yet. Beyond that, there's still another issue. So this experiment wasn't really constructed with the idea of observing this kind of quantum optics. So basically, in this particular configuration, you have an atomic ground state and an atomic excited state. Only the ground state is trapped. Okay, so once you go up to the excited state, the atom kind of goes crazy in terms of the motion, and that probably has some effect on how close you can get to 100% as well. But again, even that hasn't been quantified carefully in theory either. Yeah, so there's a number of reasons why you would not expect to get truly to 100%, but it hasn't been completely, the details aren't completely understood.
In terms of distance compared to the wavelength, how are we? Is it smaller than, so it's probably smaller than lambda?
Yeah. So
Lambda over 2.
No, I believe it's 0.6 lambda. 0.6, 0.7, something like that. Any more questions?
So for the shift in first frequency, like how much it is, like it's maybe like
No, I think it's a small fraction of the natural line width, but I'm sorry, I don't know that number offhand. Okay, so maybe now is a good time to conclude, but let me just give a brief preview for next time. So again, like the mirror is just a classical linear optical effect. But then, here I've kind of artificially restricted myself. I say I send in very weak light, so at most there's one excitation. But it's not like photons are a limited resource in the lab, right? I can easily just crank up the laser intensity. So what happens if I do that? Would I expect to see some kind of optical nonlinearities? That's not completely unreasonable because these are not classical particles, but they're two-level systems. So each two-level system can fundamentally only scatter one photon at a time. And if we're lucky, maybe these nonlinearities are even strong at the level of single photons. So maybe sending in one photon versus two photons can have significantly different effects. If that's true, then I can maybe imagine using this array. I can send in two photons, I can entangle them, start to build quantum gates for photons, and so on. So that's where I'm going to end today and where I'll pick up tomorrow.
Any more questions for us? A technical question on the manual experiment. So you have the heating effect mainly when you're on resonance, right?
Uh-huh.
If they scan that quickly, you will see some asymmetric spectrum of the. You get more. So do they study? So they have to ramp up to get this very symmetric spectrum. They have to ramp up very slowly or something like that. No?
Oh,
You know what I mean?
yeah, I know. I know what you mean. I actually don't recall the details of what they do.
If there's any interest of getting that hysteresis cycle kind of, like to get something that is reflecting that a lot at the beginning, then turn the light on for a long time.
Uh-huh. Yeah, I don't recall the experimental details. Oh, yeah. So actually, this spectrum here is the product of many repeated runs.
Any more?
Sorry, one question about the optimization of the C, the factors in front of your states. Once you optimize it, you get your minimal error. What do those factors say about the states that give you that minimal error? Is there some sort of intuition you get about the states that couple best?
Yeah. So let's see. So we have a paper about the topic. In that paper, I think we have a really nice figure. Unfortunately, I didn't really include it here. But let me see if I can try and so you have to kind of be imaginative. But basically, the idea is I can avoid, so basically, recall that free space modes, by definition, have a k vector that's smaller than omega over c. So my goal is to ensure that in the dynamics at all times, I avoid creating such wave vectors. The issue is that anytime, so imagine I have some kind of k vector, so some guided mode that's propagating through the system. If I see any type of discontinuous interface, that interface adds all kind of momentum components, right? So basically what I want to do is kind of smooth out that discontinuity. So if you actually monitor the spin wave itself in time, like in the simulations, if you actually kind of make a movie of this, what you find is that if I were to just kind of if I were to make this control field spatially uniform, the spin wave would kind of propagate smoothly, but then here it just kind of sees a kink. So it develops a kind of kink in the shape, And that kink has wave vector components that now scattered into free space. So basically, when I play with this kind of control field shape, now when you run the movie, what you see is that this kind of spin wave smoothly propagates, but then as you hit the edge, it kind of smoothly deforms. So you avoid any kind of sharp features in the spin wave itself at any moment in time. So that's the kind of intuition behind this kind of exponential gain.
Okay, I propose to stop here and then start again at 11:20.
So, sorry, there were actually like a lot of great questions today. I don't really know. Like, it's hard to say which one is I mean,
We have one more lecture to decide.
well, I mean, but there's actually so many good ones today. So I feel like I should give this out today and maybe give out another one tomorrow. I don't know. I mean, well, yeah. Again, like they were all really interesting questions, but maybe one interesting one in particular was, if you just look at the spin model, how do you tell that there's some kind of exponential gain in the first place instead of n to the 4? I forgot who asked that. Okay, right.